Okay. Chapter 12, you're reading about particle in a box again. We're going to have this wave function. I think we even had that on the exam. Right? I didn't have you normalize it, though. We're going to normalize it here. Instead of using big N as a normalization constant, I'm using big C. But Kevin, how do you start this out again? We want to show that big C is going to be the square root of 2 over L. Yeah. Yeah. Well, C times this whole thing, right? What are my limits? Alyssa, what are my limits of integration here?
0 to L.
0 to L. Kind of tell you right there. Okay. So what'd you do now, Gloriana?
You pull out the C.
Yeah, well, C squared, right?
Oh, yes, you're right. No, I didn't do that.
And then, Mel?
You're left with sine squared.
Sine square. And I should have copied and pasted a little trig relation there, Jeffrey, but I forgot. Do you remember what it was? It was something like sine square. How did that go?
Sine squared AX.
It's 1/2
Cosine.
1 minus
Minus
cos.
cosine.
Where's the A though? Do you remember this? Oh man, you guys have a better memory than I do. All right, that looks right. Does everybody agree? If it's wrong, we're gonna screw up the whole thing. We should have an equation sheet, hopefully.
It's minus cosine 2.
Excellent. Okay, so sine square AX is 1/2 times 1 minus the cosine of 2AX. So, Jeffrey, she helped you out. So how are you going to do this? What are you going to rewrite here? I'll write the C squared part for you.
Then the integral 0 to L. 1/2.
But let's pull out the half over here.
Okay, and then.
Oh, you know what? Let's see if you can envision this. Let's pull out the half and make it 2 integrals.
Okay, so.
I'm going to skip some stuff here.
The integral of 0 to L of dx.
Perfect.
Minus the integral of cosine 2 n pi x over L.
Yeah. Yeah, because my A, good, I'm glad he saw that. Here's my A. Here's my A. Oh, and we got to have our brackets. Oh, we forgot our dx. 0 to L, right?
Won't that cosine just be 1 though? Because it's n 2 pi, so it's always going to go 2 pi around. It won't just be 1. Oh, but then it has the L.
All right, L's going to mess it up. Your limits won't always be integers. And it's not going to be cosine. It's going to be, take the antiderivative. Okay, so Kevin. But I think that's a good stopping point. You guys can see how to do the rest, right? We'll come back and finish it. We'll come back and finish it if we have time. Show that. So that's another you do. We can come back and hit the you do's if we have time. Show that delta E. The delta means what again, Gloriana?
Isn't that X, Y, and Z?
Oh, we had this one. That meant dx, dy, dz. That was del. But this guy is delta. So what does that mean? Delta E. Final minus initial. Just change. So the change in energy, final minus initial. Show that it has units of energy. Okay, so is joules, 3 lines means defined, that's why I have 3 lines there. Is joules the same as, on one side, the same as the other? H, there's n plus 1. Is n going to have any units? No, it just says it's an integer. Fine. H, Alyssa, what were units of H?
Joules per second.
Joules per second or joules times seconds? And that's be squared. And M, Gloriana, M has units of?
It's just mass.
Yep,
Kilograms.
kilograms. L, Mel?
Oh, meters.
Meters, but it's squared, so meter squared. Okay, so that's another good you do. So you see what you got to do. You got to put in what a joule is and cancel stuff or that kind of thing, right? And how do you get what a joule is again? What was a simple equation to help you remember? At least that's how I do it.
Newton meters.
Yeah, it's a Newton meter. But I remember it this way because work is force times distance. And work is joules, so that means a joule has to be a Newton meter because force is newtons, use meters. And what was a Newton again? I use F equals ma, right? So Newton, Kevin, is kilograms times meters per second squared. That's how I remember that stuff. I don't know if that helps you or not. Because little a is meters per second squared. Little a is acceleration, like gravity. For each function, find the most likely locations that the particle may be found. So we're talking about these. But if you take the word wave function out of there, how did you find minima and maxima of a function? What do? You can graph it, but that's going to take you guys forever to do homework that way. Don't graph it. Second derivative will work, but that's more for, is it a maximum or a minimum? You took the first derivative and you set it equal to 0. Now why does that work? Because what's a derivative again? Anybody? What's a derivative?
Slope.
A slope. So if the slope is 0, I mean, I don't care what plot you're drawing. If the slope is 0, right? Where's the slope 0 on that funky, weird-looking plot? Right? Slope being 0 means it has to be going like this, right? That's a slope of 0. So I see a slope of 0 right at this point. I see a slope of 0 right there at that point, right? Inflection, meaning it changes curvature, right? That's second derivative. But let's just do first derivative. It seems easier. So find that slope of that line and set it equal to 0. So we have to take the derivative and set it equal to 0. What's this A doing in there, Mel?
Just chilling.
Yeah, just chilling. Is it a variable?
It's a constant.
Yeah, some number. Who knows what the heck it's even doing in there, right? And then the L, Jeff?
The length of the box.
Yeah, so again, another number, right? Okay, so we're taking the derivative. That's why I wrote d dx. I kind of skipped ahead, and I probably shouldn't have done that. Because I know x is my only variable. And they're kind of telling you. X is your only variable. Okay. So, Kevin, how do I take the derivative of that thing? What would you do? I would pull out that 48a and just, do you even leave it? I mean, do you even write it again? All right, just divide both sides by 48a, it's gone. There's no sense in even writing it. It'll make it easier to see. All right? So Alyssa, he handled the 48A for you. You still got to take the derivative of that cosine. What would you get?
Sine.
Sine or negative sine?
Negative
Negative sine.
sine. Pi x over, wait, yeah, pi x over L. Would it be 1 over L? Or no, it would be pi over L.
Pi over L. Good. Everybody agree?
Mm-hmm.
Okay. So I can make this simpler, Gloriana, and just write what? 0 equals?
Simpler.
You have to figure out where this function is going to be 0. And with that, it'll be easier if you simplify this. Just like the 48A, why'd we erase that?
Divide from the other side of the 0.
Yeah. So do the same again.
So you divide the pi L.
Yeah, pi over L, and also the,
Sine too.
not sine,
Oh, the negative.
the negative sign. So it would just be what?
Sine pi x over L.
Perfect. Okay, Mel, she cleaned it up for you as good as she possibly could. Where is this? Now, the unit circle is the way to go. This is the kind of thing you want to do in your head. So on the unit circle, in terms of this pi stuff, Mel, where is the sign 0? What would you say? What degrees in radians? What?
0.
0,
Pi.
pi,
2 pi.
2 pi,
3 pi.
3 pi, and this keeps going, right? Everyone remember that? Okay. So Jeffrey, she's got you going. She's got you started. Where's this thing going to be 0? Where x is what?
0.
0 is the first one. X is 0. Because you put in 0, you get sine of 0, that's 0. Okay, Kevin, the next 0.
Pi.
You say pi, then you're going to have the sign of pi squared over L. That's not going to work. You want to end up getting pi, right? So that means x would have to be, if x is 1, you have pi over L. You want x to be what? So you end up getting pi in this thing. You want x to be, anybody see it?
L.
L. Make x be L. Then you've got sine of pi, and that's 0. Okay. Alyssa, the next one.
I don't really know the unit circle, so.
What? Like, okay, remember it. Let's review it. So I would know this. We might very well have a quiz on our concept preview next class period.
No, Doctor.
This is a good one. So remember, the sine is always the length of which side? The y-axis, and the cosines are always the length on the x-axis. So how does this go? Well, this could be 0, or 2 pi, or 4 pi, right, or 6 pi. Evolutions of 2 pi all the time. That means over here is pi, or 3 pi, or 5 pi, right? Then up here we're going to have, it's easier to see it the first go around. If that's 0 and that's pi, the other one must be pi over 2. And then to make a whole circle around there, add 2 pi to it. So pi over 2 plus 2 pi is
2 pi over
5 pi over 2, right? Because you have to add 2 pi, add 2 pi plus pi over 2, right? So you're going to have 4 pi over 2 plus, that might be easier to see, just write 4 pi over 2, right? Because there's my 2 pi, and 5 pi over 2. So you have 5 pi over 2. And this keeps on going. Same way on the bottom. Make sense? Oh, wait to see what this one is. What's this angle? 3 pi over 2. So it's probably, 7 pi over 2. Okay, and it keeps going. Okay, so what's the next one here? We didn't finish this. 0, L. So L was where we said it was pi, right? L is our pi. our next zero for sine. Now, see what we're doing here? We started here. Here's a 0. And then we jumped over to this guy. That's another 0 for sine. Now we're back over here again. So it has to be 2 pi, which is going to be 2L. All right? And notice how it just keeps going. This is one of the mathematical ways how we're going to start quantizing energy. But okay. And you can just keep going on forever and ever and ever. But remember, x has a maximum. Well, how big can x be? What's the maximum value x can be? It's L. So can 2L be a choice? No. So you're supposed to have stopped at L. But I just wanted you to keep going to realize it. Does that make sense?
Yes.
So cross out that one. Just 0 and L. So then we need to do the same thing now with B. So take the derivative and set it equal to 0. And see if you can figure out where the zeros are. Where the maximum or the minimum of this function are. And that's at the zeros. Where the slope is 0, sorry. Anybody get some answers? L over 2. Good, because now we're looking for these guys. We're looking for top and bottom, because that's where the cosine is going to be 0. That's the side of the triangle is going to be 0 at pi over 2 and 3 pi over 2. So if x is L over 2, you get cosine of pi over 2, which is 0. Okay, that's a good one. Are there any others? Now remember, the x can only maxes out at L, so is there another one?
3L over 2.
3L over 2. The L's cancel. We get 3 pi. Cosine 3, yeah. Is that outside of our box, though?
Oh, yeah.
Because that'd be 1.5 L. Yeah. Whoops. But that's the thinking. Good. That's how you're supposed to do it. In order to stretch a spring, a force F is used. There are corresponding, who remembers their general physics? F equals what times what, stretching a spring? Kx. Where blank is called the force constant, K, or spring constant, right? What are the standard metric units for that force constant? Just use F equals Kx to get it. And solve for K. K would be what over what? Newtons over. You know what x is? Meters. X is distance, right? X is the displacement. So newtons over meters. Right? Because K is F over X. The relationship between period and frequency. Now F, sometimes we use frequency as that symbol, right? But the book is using frequency as little f, so that's what we're going to do too.
Inverse?
Inverse. F is 1 over T. The relationship between frequency and angular frequency, omega, is. See, we're going to go from what this is doing, well, write the equation first. So what times F? Anybody know?
Okay.
2 pi. And all you're going from, what was a common unit for frequency? Do you remember?
Hertz.
Hertz, right? We're talking about hertz. And which symbol is hertz? Is it omega or is it F?
F.
It's F. F is the frequency we've been messing with through all of general physics. F, hertz, per second, revolutions per second. All right? That's the F. That's the F and E equals h nu, hertz. Okay? So what we're trying to get into with omega is let's start using the unit circle and have revolutions described with radians. So that's all it's doing. Okay? But it's a little more useful when you start talking about motion, repetitive motion, to get things into radians. So that's why we're starting to introduce it. How is F related to the length of a pendulum? Man, that's a hard question. You remember that?
Is it like 2 pi square root of n over L?
I don't think this was in Star Trek. I remember Kirk had to make gunpowder in Star Trek. I don't think he ever had to mess with a pendulum. But F is 1 over 2 pi square root of G over L. G is what? Gravity. So it depends. This frequency of this pendulum is going to depend on the planet you're on, and it also depends on L, which is the length of the pendulum. So you have this little guy swinging there. So does it look like, what's kind of interesting here, I think, you almost have to have a pendulum swinging here. Does it matter how far you pull it out for the frequency? If it did, it has to be in that equation. The only way to change the frequency is to change G or to change the length of the pendulum. Does it matter what's hanging on the bottom of that pendulum? No. So it'd be a good thing for Captain Kirk to use if he had to figure out what planet he was on. Right? He'd have to have a calculator or something probably, since he's really good. Oh, how is omega related? Right, you just bring 2 pi over to the other side. Omega is 2 pi f. But then you're just left with the square root of G over L. So omega is the square root of G over L for a pendulum. Show that this expression has units of energy. Okay, so we're getting into some funky variables here. V plus 1/2. Any units there? No. Now what is this? H with a line through it. Planck's constant over 2 pi. Good. So that has units of joules per second or joules times seconds? Joules times seconds. Does 2 pi have any units? No, so just joules times seconds. And then omega. What units does omega have?
You want to use the value or the frequency?
It doesn't. Omega is omega. Doesn't matter what equation you use.
So hertz, revolution per second?
Kind of. With the 2 pi in there, you're supposed to. This is where things get kind of confusing to me, is how units can just disappear on you. Whenever you use omega, they like to say radians per second. And I think they say that, or the book or the article or whatever says radians per second because they want you to realize they're talking about revolutionary motion, the circular motion type of this repetitive motion sort of thing, and that you're in radians, so mess with all the characters there, not degrees. But when you multiply radians per second times something, they just disregard radians. It's gone. So really all that's there is the per second. Kind of a long story to explain that, but so whether it's I guess what I'm saying is when you see F, they talk about hertz or per second. When they talk about omega, you'll very often see radians per second, but the radian disappears. It's really not a unit. It's unitless. It's not there. It's weird. Show that omega equals a square. Well, see how the seconds cancel. You get joules. You're done. Right? Show that omega, which is the square root of k over m, has units of frequency. So to do this, Jeff, you're going to put in what for k? Newton meters. Newtons over meters. And then for m, you're going to put in what, Kevin? Kilograms. And then get stuff to cancel out. And hopefully, then you have to take the square root of it. So hopefully you end up with 1 over second squared in there. Okay, so that's another you do that you can wrap up. What does AMU stand for? Atomic mass unit. Good, atomic mass unit. Okay, now I don't know if anyone brought a book here, but what numerically in kilograms is an AMU equal? If you have carbon-12, what's the molar mass of carbon-12? 12, right? Why isn't it 12.01? Go ahead and look at the periodic table. Big C is 12.011, blah, blah.
Why isn't it?
Yeah. Why did we just say, why did Kevin say 12? And I said, oh, he's right.
Is this an easy question? Or are you like going really in depth?
No, I just want to make sure we see the assumption. What? Why does it say carbon? Why on carbon does it say 12.01? I don't even remember the number. 12.01 something. 12 point what?
12.0107.
0107. It keeps going maybe. Why did it say that? Anybody?
The average.
Average of what?
Isotopes.
The isotopes. See, you know this. The average of all the isotopes. So what all they're talking about in this definition of AMU is that carbon-12. So everything's based on it. So then you have this nice round number. Okay. So if you have 1/12, so the molar mass of carbon-12 is 12 grams per mole, right? And then if you want 1/12 of it, that's how many grams per mole? 1. But 1 gram per mole. But they want 1 AMU, so they want essentially 1 carbon-12 atom, or 1/12 of 1 carbon-12 atom. So really all you're doing is dividing that 1 gram per mole. How do you get it into, how do you get the mass of 1 atom? Divided by what? Avogadro. Right, so where this whole thing started, it started with 12 grams per mole. Then they said, oh, we want 1/12 of it. And then you're in 1 gram per mole. And then you have to divide by Avogadro. 6.022 to the 10 to the 23rd. And then you'll get grams, but they don't want it in grams, they want it in kilograms, so I'm not done yet. Divide it by 1,000. Okay, you do all that, yeah, that's your answer. I don't know.
Will it be around the mass of a proton?
Let's find out. We'll find out. Because the mass of the proton, you need a book to figure this out, though. And here's my book. bet you I wrote down the answer here somewhere. No, I didn't.
I didn't bring my calculator.
So what did you get?
1.67 times 10 to the negative 26.
Well, more digits though. Who knows what we're gonna need?
1.6605.
Whoa, shit, shoot. 1.6605.
77.
Okay, times 10 to the
Negative 27.
kilograms equals 1 AMU. Okay, you should probably write that. If you have your book, write that on the inside front cover or somewhere. The reason, oh, I did. The reason why I did it is because I guess that's not quite the inside front cover. But look at all these nuclides, right? And then they give you the M/U. So remember, this author has a weird way of making tables. They have their variable, and then they have slash the units with the variables in. Remember that? So here's all these masses of all these nuclides, but in units of U, which is an AMU, according to this thing, right? Well, AMU is a U. Okay. So we got number 11. Oh, there it is. We're on number 12 now. AMU is a U. So what is the atomic mass of 35 Cl in units of U? So you find chlorine. Where do you see chlorine? Here's chlorine. They're talking about chlorine 35 or 37?
35.
35. Okay, what does that say, G?
What, that number?
Yeah, chlorine 35. So read it out loud so everyone can write it down.
34.9688.
34.9688. And that's just on the inside front cover. Okay. And the whole purpose of doing this is so you can get, it's supposed to be easier to get this sort of thing. So now what's the mass in kilograms of a single chlorine 35 atom? We're going to use our conversion factor here. Because we know 1U is 1.660577 to 10 to the negative 27 kilograms. So we can convert these U's into kilograms. Because all these tables are in U's. So that's the purpose of doing all this. So what's the mass of a single chlorine 35 atom? We know it in U, but in kilograms it will be. What'd you get? Did you get an answer?
I got 2.1058 times 10 to the 28.
10 to the negative 28?
Oh, probably 28.
What do we do?
Oh, I did not.
That should be.
Oh, okay, so it's 5.
Look at it this way. That many kilograms per U. Right? So they use cancel.
I divided, so it's 5.8067.
That's right. 5.8
times 10 to the negative 26.
kilograms. Anybody else get that number?
Yeah.
Okay. Right. So this is going to be a useful thing to have. That conversion right there. Euler. Mr. Euler. They might be able to come back and do our U-dos. Euler's formula can be written as e to the I phi is cosine phi plus I sine phi. Use Euler's formula to show that the integral from 0 to 2 pi of e to the I phi d phi is 0. So, Alyssa would probably just do what to show this?
You just replace that E
Yeah, e to the I phi.
with the cosine b plus.
Yes,
cosine
that's what I would do. And then break it up into how many integrals, probably, Kevin? Two. Should work,
Could you
right?
derive it first, and then after you finish deriving it, replace the e to the I phi with cosine?
Derive what? What do you mean?
Like derive the e to the I phi as it is, and after you derive
Oh,
it, put
take
in-
that. I don't think so. Oh, but then you're not using the relationship. E to the I phi, take the antiderivative, put in 0, put in 2 pi. Oh, because you can't evaluate e to the I 2 pi. You can't evaluate that.
I'm saying after you take the derivative, replace your e to the I phi with cosine phi plus, like after.
Oh,
you derive it.
after you, I don't see why not. Either before or after. I think, I wonder. It shouldn't really matter. Because you're saying there might be less work to do. It's a lot easier to take the antiderivative of e to the I phi than those two. I didn't do it the other way.
I'll try.
Try it.
If you just integrate it into separate integrals, can you pull out that I?
Because the I is a constant. So any constant you can always pull out of an integral. But you can't pull it outside of an exponent. You know, it's in an exponent, you can't just pull it out. Or if it's inside a sine or cosine, you can't just pull it out. You got to evaluate, though, from 0 to 2 pi.
Oh yeah, I forgot about that.
Now, when you
right?
pull that out, though, then there has to be an I here, so that won't work. So what you have to do is break it into integral here and break it into an integral there.
So then when you integrate this, do you just leave the I there?
And I would leave the I outside the integral.
Okay, like it's a constant, and then just evaluate sign.
Yeah.
So this will be
It works.
Yeah.
I just distributed.
Put 0 out.
Yeah. 0 out.
All right. And just go on from there. So you should get
Yeah, you get 0.
0. One of them, I think you get 1 minus 1. I think that's what happens with the I part.
One of them is 1 minus 1, and the other one is I minus I.
Okay. How about this reduced mass thing? What is this for? What was this? We had these equations in physics like F equals ma and this kind of stuff. I don't know if you got to the point in physics where you didn't use little m anymore. Instead, you use this symbol. Did you? What it's for is for circular motion especially, when you have multi-bodied objects, not just a baseball flying through the air, but one ball tied to another ball or something, right? Two objects moving through, rotating or flying through the air or something. So one is mass A, the other one's mass B. And how you write that is the reduced mass is mu. Well, it's 1 over mu is 1 over ma plus 1 over mb. If there's two of them. Now this is going to happen a lot. We're supposed to be using mu, but it really reduces down to either ma or mb. And the reason why is because very often one of these, like think of a molecule like HCl, one of these bodies is much, much lighter than the other one. If Ma is much, much smaller, that's what the double arrow means. If Ma is much, much smaller than Mb, which term goes to 0? If Ma is much, much smaller than Mb, or how's this going to work? Or think of it this way, Mb is much, much bigger than Ma.
MA goes to 0?
It's 1 over, though. Right, you've got this term, you've got this term. And they're saying that Mb is much, much bigger.
So MB would be a smaller number,
1 over Mb would be a smaller number,
right?
right? So they're trying to say that you don't, right? Ma is much, much bigger than that. Oh, I got it the other way around. Anyway, the point is if this guy's getting huge, you divide by a huge number, it essentially goes to 0. Then all you're really left with is this. And it never really goes to 0. But mathematically, at some point, why do we keep adding this? It's like taking 12 plus 0.0007. It doesn't do anything. You're just wasting your time. We never carry that many sig figs or something, some story along that line. So you just end up forgetting it after a while. So then Ma equals mu. So it's always the lighter one is what your reduced mass would come down to. Does that make sense? So go back and see if you can knock out the you-dos. You won't have any homework but reading.
You do what? You won't have homework or what?
Reading.